In this video, we explore what it means for a function to be concave, whether it's concave up or concave down, and what we call concavity, as well as the second derivative test for finding relative extreme values. Okay, so the first thing I'd like to do is get some definitions to you here, talk about what it means to be concave as far as a mathematical function goes, and then we'll talk about what we call point of inflection, and go through an example or two, and then explain what the second derivative test does and how to use it. Okay, so the definition of concavity here, I'm going to skip by a bunch of this kind of rigorous part, but basically what we say is the graph of a function f is concave upward when f prime, the derivative, is increasing. Okay, so when the derivative is increasing, and that's important. The second bit here, and concave downward when f prime is decreasing. Okay, so what it means for a derivative to be increasing is, of course, then the second derivative is positive, and when a derivative is decreasing, it means the second derivative is negative. Okay, and I'm trying to illustrate with these two pictures here, these two graphs. These are just of some general functions, f or g, whatever you want to call them. And we notice here that the graph on the left has a couple points here. If we go from one x to another, we notice that the tangent lines at these points are below the curve. Okay, this was what it would mean to have slopes that are increasing, right? Going from one point to the next, we see that the slopes are getting larger. The slopes are increasing. The derivative of this curve is increasing, and that means that this function is concave up over this interval, right? So that's what it means to be concave upward. The next picture, we see just kind of the reverse scenario. We've got 3 points here that we look at, and we see the slopes there are decreasing as we go from one point to the next, and that's going to indicate, concave downward. So we've got a function that's concave up and a concave down. We see these kind of two different shapes here, and actually we can break them apart into kind of like 4 different kind of pieces. You can be increasing in concave up, increasing in concave down, decreasing concave up, and decreasing concave down. So we've got kind of 4 shapes that we're going to pay attention to here and use to construct any function. Okay? And I draw these little lines here to kind of indicate how I think about concavity, right? This, if I were to view this curve as like a satellite dish or something like that, it's sending all the rays downward, okay? Whereas the one on the left, concave up, is sending all the rays upward. Okay, so that's what I kind of think about or visualize in my head when I think about concave up or down. Okay? For concavity, we're going to use the second derivative, right? Looking for whether the first derivative is increasing or decreasing is the same as looking at the second derivative of the original function. Okay? So what I want to do here is kind of explain a little further what's going on. As long as the second derivative exists on an interval, basically, in short, what we say is if the second derivative is positive for all x in I is just going to denote the interval that we're working on, okay? For all x in our interval, if the second derivative is positive, then the graph of f is concave upward on that interval, okay? And just like concave upward, you use a second derivative to determine concave down. If the second derivative is negative for all x on that interval, then the graph of f is concave downward. I typically say concave up or concave down. I don't usually say upward or downward, but I guess technically we should say upward or downward, but you know what I mean if I say concave up or concave down. Okay? Now, there is a chance that this doesn't change, right? So there's a chance that maybe I'm neither concave upward or downward. Actually, in fact, I've got an extra 1 here. I apologize. This should be bullet number 2. There's a chance that we're not concave up or down. We could potentially just have kind of no shape at all and really just be flat or constant, okay? So that's going to be a situation where the second derivative is 0. I didn't outline that here. A point of inflection is just a point at which we change concavity, okay? So this is kind of an intuitive thing to look for, very similar to what we explored with increasing and decreasing. This is really not too much different. In fact, that's really going to be where we start, is looking for places where the second derivative is 0 or undefined. Looking at places where we don't have any concavity at all, and then looking around that point. And if we have a change in concavity, that's going to be called a point of inflection. So how we say here is if f has a tangent line at some point C, there has to be a tangent line there, that's crucial. The first derivative has to exist at a point. Then if the second derivative changes sign, or if the function changes concavity. So then this point, x equals c, is an inflection point if f changes concavity at that point, okay? So for this, we're looking for the second derivative being 0 as possible inflection points. It's not necessarily a guarantee that we have an inflection point there. It's just a possibility. So I have to work with that. All right, so very similar to how we explored, like I said, increasing or decreasing parts of a function. We pretty much handle this the same way, but we use the second derivative instead of the first. Let's look at the concavity of this function here, e to the minus, in the exponent there, x squared over 2. Right? So it's kind of a bizarre function, but nonetheless, we can explore the concavity. I need two derivatives of this function. The first one is just our derivative of e to a power, which should be e to a power, times, chain rule, derivative of the power, derivative of minus x squared over 2 should just be a minus x. Okay? And I'm just going to kind of recollect this a little bit, make it look nicer. Minus x e to the minus x squared over 2, because I need a second derivative. Okay, I'm going right towards concavity, right? I'm not specifically asking for where the function is increasing or decreasing, so that part I don't care so much about here. Second derivative, I'm going to need product rule because I've got two functions of x multiplied by one another. So my second derivative then should go, the first is minus x times the derivative of the second, and again I see this same piece again, e to the minus x squared over 2, chain rule times another minus x. Okay, so that's the first part of my product rule. Second part, plus the second function, e to the minus x squared over 2, times the derivative of the first. Derivative of minus x is a minus 1. Okay, and I'm going to try to simplify this as much as I can, clean it up, factor as much as possible, because I'm looking for when this second derivative is equal to 0. Okay, so I factor out, and e to the minus x squared over 2, I've got a missing minus there. So this should be then e to the minus x squared over 2 times x squared minus 1 as the factored form of my second derivative. Okay, so this guy I'm going to set equal to 0, solve, and then try to figure out where this second derivative is positive or negative, and then what that says about the original function. So I set this guy equal to 0, and I make some analyses. I solve this equation here. E to the minus x squared over 2. I've got an exponential there. That guy is never going to be 0. It's the same as 1 over e to the x squared over 2. And e to the x squared over 2 for any x is not going to be negative, right? So 1 over that is not going to be negative. This is always going to be a positive quantity. So for solving the equation where e to the minus x squared over 2 would be 0, I get nothing from that, right? I can exclude that portion, leaving me with only x squared minus 1 to be 0 to make that expression equal to 0. So solving that gives me x is equal to plus or minus 1. Okay, so I've got two potential inflection points, and I'm going to put those on a number line, a sign chart, just like we did for the first derivative in the previous video. Okay, so here I've got 2 points, 2 x values that I'm interested in and mapping around. This breaks up my interval into 3 sub-intervals, minus infinity to minus 1 to 1, and then 1 to infinity. Okay? And again, just like before, I need 3 test values, 1 in each of these intervals. Let's do minus 2, 0, and 2. And I'm going to plug those into my second derivative to tell me what's going on with the original function, okay? So for each of these guys, I'm going to plug things into my second derivative, and I'm going to use the factored form in the red box there. So plugging in -2, again, the outside portion, that e to the minus x squared over 2, is always going to be positive. So I've got a positive quantity on the outside. I don't really care what happens when I plug in -2, that's going to be positive, and I can handle that ahead of time. I've got a positive on the outside with this exponential, and the rest, x squared minus 1, it does depend on what I plug in there, but plugging in a -2 gives me a 4 minus 1, and that's going to be a positive quantity. So the second derivative on the interval from minus infinity to minus 1 is positive, which means my function would be concave upward. Okay? It might not make a complete U like that. That might not be the exact shape of the curve. It could maybe be like this or like this, for example. But it's concave upward nonetheless. Okay? So I just make that indication. I know it's concave upward on that interval. I don't know exactly the perfect shape. I don't know if the function's increasing or decreasing there, but I know it's concave upward, and that's what I'm asking. The next interval, from -1 to 1, I plug in 0 to my derivative, and I see that I get a plus and a minus because the exponential is positive, and 0 minus 1, 0 squared minus 1 is negative. So on this interval, I am concave downward. Last but not least, I plug in the 2 that's on the last interval from 1 to infinity, and I'm going to see another plus and plus, giving me concave upward. Okay, so I've got 2 intervals where my function is concave up and 1 where things are concave down. Okay, so I'm concave up on the interval from minus infinity to minus 1, and then again from 1 to infinity, and I join those together with that union symbol, that U, not to be confused with concave up. I then have concave downward from -1 to 1. Okay, easy enough. Now, also notice that I switch concavity as I pass from one interval to the next for all 3 of my intervals here. Going from -1 across -1, I switch concavity. This guy is an inflection point because I change concavity going across from the minus infinity to -1 interval to -1 to 1. Crossing that point, I go from concave up to concave down, and thus I've got a point of inflection point for short. Same thing on the other side. I've got another inflection point at 1. Cool. So what I'm going to do is I'm going to bring up a graph of this function here, and I'm going to try to indicate where everything is happening, plot some points, and show you exactly what this graph looks like. Okay. So here we have what our function looks like, and I've got that I'm concave downward on the interval from -1 to 1. So I've plugged in those points. I've plugged in 1 and -1, and we see the corresponding values there in black. I've also divided up my picture with what looks like vertical asymptotes, those blue lines there, the dotted lines. That's just to indicate where my sign chart was, right? I've split up my sign chart around -1 and 1. So that's why I've indicated those guys. We see the inflection points plotted there, and I see the concave downward portion in the middle, right? That satellite dish kind of that's all pointing downwards, right? It looks like a cap. On the other sides of -1 and 1, I see concave upwards, right? I see this kind of upward portion, and that's where the second derivative was positive on either of those intervals, okay? So those are the corresponding shapes that we see. Like I said, it's not like a complete U, but it's just a nice little shape that's concave upward. And if I were to shine a light, it would kind of bounce back up in both of those sections of the graph. So these guys are my inflection points, and I find their heights. I find the y values by plugging those into the original function, right? -1 e to the -2 and 1 e to the -2. That's that 0.607 that you see is e to the -2. I get that from plugging in 1 and -1 back into the f of x. There you see at the top left. I also want you to note that there is a horizontal tangent line when x is 0 here. All right, so right at 0, that looks like there's a maximum there. But also notice that my function changes. If we were to use the first derivative test, we would see that the function changes from increasing to decreasing around that point. I don't really even need that information here. Since I have a horizontal tangent line and the concavity is downward, I want you to note here that f prime of 0 or f double prime of 0 is negative and the first derivative is 0, giving me a horizontal tangent line, and I'm concave down. This should be a local max. Okay, so we have a nice little indicator using concavity to determine that I've got a local maximum there at this flat portion, right at that horizontal tangent line. That's kind of a key part to this section. We're going to explore it more in the next example here. Okay, so moving on, I've got then another example here for you. Function is x squared plus 1 divided by x squared minus 4. Okay, so this guy I want to explore a bit. I've got the original function there and the first derivative, and I'm going to use that first derivative to find the second derivative. Oh, no, I'm sorry. That is the second derivative. I apologize. So I've got the second derivative there for you. I've done the work already, and I want to use that to find the concavity. I still need to solve the second derivative, right? Or I need to set it equal to 0 and solve. So I'm looking for the potential inflection points from the function there, from the second derivative. So I set that second derivative equal to 0. A fraction is 0 when the numerator is 0. So I set 10 times 3x squared plus 4 equal to 0. And both of those quantities, both the 10 and what's in parentheses there, 3x squared plus 4, are positive always. I can't plug in anything for x and somehow make 3x squared the same as negative 4. This is never going to be 0. The only time that my second derivative is going to be give me anything useful here is when it's undefined, and that's going to occur when this denominator is 0, x squared minus 4 to the third power. Okay, and in fact, the third power doesn't really have much of an effect because when I raise a 0 to the third power, I still get 0. So what's really going to take control here is when x squared minus 4 would be 0, and that of course occurs at plus or minus 2. Okay, so plus or minus 2 is when the second derivative is undefined. I want you to look back, however, at the original function, and we see that the second derivative has the same denominator shape there. The original function, x squared minus 4 on the bottom, is going to give me domain issues, right? It's going to give me vertical asymptotes. Those aren't the locations of inflection points. There's actually nothing there, all right? I've got those imaginary vertical lines that I cannot cross. I've got domain issues at plus or minus 2. So how we handle these, they still go on our sign chart. They go on our sign chart because they break apart the function, right? I can't cross those vertical lines, but it's important to note that they're not inflection points, okay? So I put those on my sign chart, just as I would have with potential inflection points, but I draw these little dotted lines to indicate that there are vertical asymptotes, okay? So when I go to make a rough sketch of my function, it's going to be important to know that those are asymptotes. But I'm still looking for concavity, so I still want to break apart and write down these subintervals here, and then make sure I test points in each of these subintervals to determine the sign of my second derivative. So I'm looking for numbers between minus infinity and minus 2, so like a minus 3, 0 between negative 2 and 2, and then a 3 on the interval from 2 to infinity. Those are my test values. Again, those are the numbers that I'm plugging in, okay? And as they're going to basically represent what's going on the entire interval. Same process as the previous example, plug these into the second derivative. So my second derivative is a quotient, so I'm going to look at the numerator and denominator respectively. We talked about a little bit before that the numerator was always positive, and that's going to remain true no matter what I plug in. But nonetheless, let's see what happens when I plug in a negative 3, I've got in the numerator, negative 3 squared is 9 times 3 is positive, plus 4 is still positive. I don't care what the number is. I've got a positive up top. Okay, you can go through and actually type that into a calculator or do the arithmetic by hand or in your head and get a number there, but ultimately all we care about is the sign, positive or negative. Denominator is where we're going to get something interesting. Negative 3 squared is 9 minus 4 is positive. Cube a positive, you get a positive. On this interval, I am positive for the second derivative, which means the function is concave up. So again, it's what the second derivative is telling me about the original function. So when I say it's positive, I mean the second derivative is positive, meaning the function is concave upward. From negative 2 to 2, I plug in 0 to my second derivative, and I get a negative then in the denominator because 0 squared minus 4 is negative. Cube it, I get a negative back. Okay, plus divided by minus is minus. That's why this interval from minus 2 to 2 has a minus sign, and thus why the function is concave downward. Last but not least, I plug in 3 again, and we're actually going to see the same effect as what we saw with negative 3 because both of the x's are squared there. So I get another positive, and again, concave upward. Okay, so I've got no inflection points here, but I've got 2 intervals where we're concave up and 1 interval where we're concave down, just no inflection points. Okay, plus or minus 2 are not inflection points, even though I'm changing concavity around those points. I still have asymptotes there. So again, I'm going to plot this function here and see what it looks like. And then I'm going to also indicate where I've got those concavity. So again, I see the vertical asymptotes there at plus or minus 2. I'll put those in a minute. But on each of these portions here, I've got concave up, and then the red down there is where I'm concave down. Okay? These two guys, even though I'm changing concavity around these points, these are asymptotes that I'm changing concavity around. So I can't have inflection points at minus 2 or 2. Again, notice a horizontal tangent line there. Again, the conversation about concavity is basically done. I've got a horizontal tangent line at x equals 0 is what it looks like. I've got that point there, 0 minus a fourth is what we see. There's a horizontal tangent line. There's a flat point there, a flat tangent. And I notice that the function is concave downward. The derivative is 0 there, horizontal tangent line. That's what that means. But I've also got a second derivative that's negative at 0. So I wrote the first derivative there so you can see where that 0 comes from when I plug in 0 to the first derivative. But the second derivative is negative when x is 0. Therefore, I can say that that point, that critical point, should be a maximum. So when I plug in 0 to the second derivative, I get negative numbers, which means I have a relative maximum because I'm concave down at x equals 0. This is actually, and I alluded a bit to this in the last example, this is what it means to use the second derivative test. This is the basis for what the second derivative test is going to tell us. At a critical point, at a place where the tangent line is horizontal, if you are concave downward, you've got a relative max, and if you're concave upward, you've got a relative min. I'm going to outline that here next. Second derivative test tells me that if the derivative is 0, and as long as the second derivative exists, then I've got a couple cases that come up. If the second derivative at C, at the place where that tangent line is horizontal, if the second derivative is positive, my function is concave upward, and I've got a shape that looks kind of like this. Horizontal tangent line, concave upward. I've got F being a relative minimum at that point. Concave upward, relative minimum. So it might seem a little backwards, but once you've got the shapes down, it makes pretty good sense. Horizontal tangent line at the same time being concave up should indicate a minimum. Just likewise, but in the other direction, if my function is concave down, if the second derivative is negative where there's a horizontal tangent line, concave down, horizontal tangent line, I've got a relative maximum at that critical point, at that horizontal tangent line. Of course, there's a potential to have a horizontal tangent line and not have any concavity, okay? So if that's the case, if the second derivative is also 0, then the test is inconclusive, okay? If this happens, we want to use the first derivative test. A situation where that might occur is something like this. I've got a horizontal tangent line somewhere. It's kind of like a shelf, but I'm neither concave upward or downward. Okay, this is the place where you might have an inflection point, but you aren't necessarily going to have a max or a min. So those situations do exist, and we can find them pretty easily, but the second derivative test might not work for you there. Let's do an example where I use this second derivative test. Here I've got a function minus 3x to the fifth plus 5x cubed, and I want to determine where the relative extreme values are. I'm going to look for relative maxes and mins with the second derivative test. So I need two quick derivatives, but first I need to find where the first derivative is 0. So I take a first derivative there, minus 15x to the fourth plus 15x squared. And I set that equal to 0. I'm going to factor this guy first. So I see a 15x squared in common, leaving me with 15x squared times, and I'm going to switch the order of the terms, 1 minus x squared. Switch the order just because then I don't have any minus signs out in front of anything. It's just a little bit easier on the eyes. But if you distribute that back in, you get exactly what we started with our first derivative there. Set this guy equal to 0. Once I factor a little more, I see the difference of squares there. 1 minus x squared factors a 1 minus x to a 1 plus x. Okay, set it equal to 0. I've got 3 potential maximum and minimum values here because x squared could be 0, 1 minus x could be 0, and 1 plus x could be 0, giving me 3 potential candidates for maxes and mins. X is 0, 1, and minus 1. Okay, to test each of these, we have our first derivative test. Of course, I can see if my function changes from increasing to decreasing or vice versa around each of those points. I could go through that process. It's not too bad. I'm already halfway there. I could also take a second derivative. And this is nice as long as your second derivative exists at these points, 1, and 2 is easy to take. Right? Since I've got a polynomial, my second derivative is really pretty easy to do here. I've got a minus 60x cubed plus 30x. I don't really need to factor this to plug in each of these critical points, critical numbers, but I'm going to just to make these mental calculations a little bit easier. If I factor a 30x out here, I've got a 1 minus 2x squared left over. Okay. This makes plugging in my x values just a little bit easier, at least in my opinion. So when I do that, it's easier to figure out if my function is then concave up or down. So again, the second derivative test says that at a horizontal tangent line, so at 0, 1, or minus 1 for this example, if my second derivative is positive, that means I'm concave up, should have a relative min. If my function is concave down, if the second derivative is negative at any of these 3 points, I've got concave down. At a horizontal tangent, I've got a relative max. So I take each one of these guys and I plug them into my second derivative, okay? This will tell me the concavity at each one of these horizontal tangent lines. Plugging in 0 doesn't really get me much. I get 0. Right? Because 30 times 0 makes everything 0 here. The test is inconclusive, okay? So what I would have to do is figure out if my function is changing from concave up, to changing from increasing to decreasing. I'd have to use the first derivative test there. It happens. I just wanted to show you a situation where the test doesn't work. It's just not, it's not all powerful. But in the other 2 situations, we are lucky enough to get a result Plugging in 1, I see 30 times 1 times 1 minus 2. 30 times 1 is positive times a negative 1. That's going to be a negative value. What that says is my function is concave down at x equals 1. This should mean that x equals 1, I'm going to actually find the point here. I plug the 1 back into my original function to find the y value, and I get a positive 2. This is going to be a relative max because my function is concave down. Right, I've got this kind of shape there. Okay, concave down at a horizontal tangent line, relative max. I just have the actual point there. I have the actual maximum value being a 2. And again, that comes from the original function. One last one here, plug in negative 1, and we get a positive value out. So at that point, I've got a relative, I did it wrong. I'm concave upward. I wrote the wrong thing. This should be relative min. I apologize. This should be a relative min. Okay. Horizontal tangent line, concave upward. That should be a relative minimum. All right. And I've got, again, both of the points there. The actual points on the graphs are 1, 2, and -1, -2. Those are not intervals. They're actual points. So try not to get intervals confused with points. So now as a synopsis, we've got increasing, decreasing based on the first derivative, and also able to find maximum and minimum values with the first derivative test if we change from increasing to decreasing or decreasing to increasing at a critical point. We also have concavity based on the second derivative of a function, possible points of inflection if we change concavity, and then the second derivative test. If I'm at a critical point where the first derivative is 0 and my function is concave up or down, I can determine if that critical point is a max or min. All right, that's it for this video. Thanks for watching.